Guillermo, hi.
Hello there.
Glad somebody showed up.
I
There-
wouldn't.
there we
People show up.
Right.
Hey, Kevin.
Afternoon.
Afternoon, it is, yes. Oh, so where is everybody? Yeah, that I've totally revamped the this last part of chapter 9. It's really very strange what happened. I've been prompting these notes. I'm basically writing all of this fresh, but prompted by the version of this class that I gave about a decade ago. And that coordinate rotation I did is completely unnecessary. I did it in my notes. I looked at the quantum field theory book that I was referring to at the time by Maggiore, and Maggiore does it too. I see no reason whatsoever for it. It really complicates the calculation and obscures the patterns that you want to see in order to extract Feynman rules. So I've rewritten all of these examples with the scalar fields to just skip over that. They're much more straightforward now. And I may even do that first one again. No, probably best to move on. But anyway, that coordinate rotation to the capital X and lower X, the sum and difference coordinates are certainly going to be useful transformations for some calculations, but they're completely unnecessary for these. And
Are you talking about these wedge products and things that we started taking toward the end?
yeah, I threw in some wedge products, just as an easy way to find the volume element. That's the only reason I was doing that. You can multiply, right? If X is equal to X1 plus X2, then DX squared is going to have, DX1 squared and DX2 squared. Those don't contribute to the area element. But wedge products actually keep track of the orientation of your integrals as well as the volume element. So it's a really quick and easy way to get it right. Hi, Tyler.
I have a question.
Yeah, Guillermo, what you got?
So yeah, so we're doing all of this in the direct field. Would the analysis be very similar once we get to what's it called? The spinor field?
Spinor field. Yeah. We're going to do pretty much all the same things. There will be some additional features, right? I was quickly saying that. I might as well write it up here. This is getting ahead of the story, but let me answer your question. So we're going to analyze these Feynman diagrams in pretty much the same way. But all right, we've been inserting a propagator D4Q of basically this form minus I Q dot some Y over Q squared minus M squared. Something like this we've been putting in for the propagators. And that applies to a scalar field. For a Dirac field, you're going to have an integral D4Q and basically 1 over ID slash minus M, right? It's the inverse of this, probably some phase factor up here. Similar, but the way that you handle this weird thing, and this is what's 1 over a matrix. So what you do is you multiply by the conjugate here and here. And when you square this, you just get, or I'm sorry, this would be P slash. And I'm not necessarily being careful with science, but this is just going to give your P squared minus M squared in the denominator and puts the gamma matrix in the numerator. So when we have this long line of integrals, we're also going to have a long product of gamma matrices. And so that'll be the main new feature that comes from the Dirac equation. The other thing that's different in QED, we're going to be looking at, in fact, let me write this out, because this is what I want to do today. I need to order some blue markers. So we're computing P1, P2 with the, no, wait a minute. Sorry. Scattering amplitude with K1, K2. We're computing this thing. And for 2 particles in and 2 particles out, we have 1 over I times the square root of Z, but we get it 4 times. So the I's go away and we just end up with 1 over Z squared. We'll deal with how to compute that later. That just has to do with normalizing this perturbative expansion. And it turns out that this Z is something like 1 plus order lambda squared. So you don't need to worry about it at first order at all. It's really just 1, but it's just a normalization. Then we have a product of product over I of the PI squared minus M squared and the KI squared minus M squared. I'll write it this way to make it a little shorter. I runs from 1 to 2. So 2 particles out, 2 particles in. And then we have a whole mess of integrals, D4 X1 through D4 X4. And those are the X1 and X2 I'm going to take to be the initial positions of the particles, X3 and X4 the final positions. And then we have the exponential of e to the, let me see my sign here. No, I put I. P1 dot X3, P2 dot X4 minus K1 dot X1 minus K2 dot X2. Sorry, I ran out of space. And then we have this matrix element vacuum expectation of a product of fields, where we're going to have, now let me see, phi 1, X1, phi 2. So these are our various incoming and outgoing fields. And then we have the interaction Hamiltonian, which is, in this case, minus I lambda over 4 factorial. And then we have the integral phi to the 4th d4x. And then vacuum expectation down. So this is the thing we want to evaluate. Can you see it? Can you all see that all right? I hope I've written large enough. Let me know anytime I get writing too small or something. I'm trying to get a lot of stuff on the board here. So this exponential gets expanded in a Taylor series. Higher order powers. So this at each order, this is bringing in 4 more factors of the field phi. And this will be, I think I call this phi of y, d4 y. So when we get to quadratic terms, we'll have 2 y's as well as the x's. And you notice we're building up integrals with everything. We've got 4 integrals here. Depending what order we're working at here, we have 4 integrals times the order. And then each product of fields, okay, so the 0th order thing we did last time, we rewrote this as normal ordered stuff plus propagators. So we had D1, 2, D3, 4 plus D1, 3, D2, 4 plus D1, 4, D2, 3. Now, 1, 2, and 3, 4, our picture is the X1 and X2 going into an interaction region, and X3 and X4 coming out with corresponding momenta. This will be K1 coming in, K2 coming in, P1 and P2 going out, and then interactions happening here. So this first term, D1, 2, D3, 4, you know, that would correspond to a diagram where the initial particles interact and the final particles interact. Like this, you know, that is not this scattering. So this one doesn't occur. We just get these two, where X1 connects to either 3 or 4, and there's some interaction. Well, when we have 1 here, there was no interaction, and we got 0. I won't redo that one, but I have redone it in the notes. And you know, please look at the new notes. They're the new notes have a timestamp of 6:50. I alerted you that there were some new notes, and I changed them once, like 10 minutes later. So it's one small change. You know, you're fine looking at what you're looking at, but I did make one further typographical correction. But get the new notes before you dig into all of this. I've corrected the problems. You know, there were some mistakes in the problems as well. So for chapter 9, the April 13 at 6:50 p.m. version is the version you want to be looking at. Now, what I want to do today, all right, this is what you get with 4 fields in the 1. But what we want to look at today is this first order interaction. And so we're going to have 4 more fields. So we're going to have products of 4 Ds. And if you draw the picture of what can happen, well, there's one vertex. When we do this to first order, we're talking about a single vertex. Hey, Alex, a single vertex. So everything is going to come together at that vertex. X1 and X2 will meet at this vertex with a probability proportional to minus I lambda that ends up squaring. And then the scattered particles, X3 and X4, come out like this. So this is the diagram we're talking about. Now, let's see. I think there's only one version of this one we have to worry about. When you get to higher and higher orders, you have to ask whether these get interchanged, but you can't tell. They're both coming from the same place, so you don't get anything in there. But this diagram, right, if this occurs at a position Y, then we have a D, well, let's call it Y minus X2 here, a D Y minus X1 there, a D X3 minus Y here, and a D X4 minus y here. And the 4 factorial is going to cancel because those y's are all interchangeable here. They're all at the same point. They all just commute. I've been writing the future minus the past coordinate on the propagators. In fact, these are symmetric. You'll get the same thing whichever way you write them. But let's see now. 0th order, 1st order. Let me write out this case then. So so what we have, we're going to have we have 8 fields phi. They're the 4 in and out states, and there are 4 from this 1st order correction. So we're going to have 8 factors of the field. The propagators come from pairs, so we're going to have a product of 4 different propagators here. And now, what are they going to be? You know, they're going to be these. In the notes, I'm going to change this to an x5. That way it agrees with my notes. So the interaction point I'm calling x5. And so this matrix element will reduce to d, then I can call this 3,5, d 4,5, d 5,1, and d 5,2. So those are the propagators that replace this vacuum matrix element. All right. Just to say it one more time, we reorder the fields as normal ordered products times commutators. Those commutators are propagators, and all of the normal ordered products vanish. So Wick's theorem allows us to replace products of fields with products of propagators. So now let's write this whole thing out. Now the question is, how many times I want to write this whole thing out? So let me not write this prefactor. I just want to look at the integrals. So we're going to have integrals over d4 x1, d4 x2, all 4 of these. And then from the, hang on, now each of the propagators, let's see, this is going to give us a d4 x5. Then each of the propagators has the general form integral d4, and I'll call these y. Then I e to the, well, plus or minus I, some momentum dotted into y over p squared minus m squared. So all of the propagators look like this. So each one is going to bring in 4 more integrals. We've got 4 propagators, so I'm going to have d4, hang on, these are integrals over the momentum, I'm sorry, q. So we're going to have 4 more sets of 4 integrals over the q's. Let's call it q1 through q4. Let me check this in my notes to make sure I've got it right. Yeah, q1 through q4 and x1 through x5. Then we've got the 4 propagators and this exponential. So there's the exponential of I, and this is the same for all of these things, x3, p2 with x4 minus k1 with x1 minus k2 with x2, like that. Then we have the propagators. And these propagators, each of the propagators comes with a 2 pi to the 4th. So we're going to have a minus I lambda because we're at first order. And because there are 4 of these, I can just write 2 pi to the 16th. And then we have 4 factors of I, that's 1. So I won't write the 4 i's, although I've written them in the notes. And then a bunch of exponentials. E to the minus I Q1 dot. Okay, so well, any of these. So here I can write x3 minus x5, e to the minus I Q2, x4 minus x5, e to the minus I Q3, x5 minus x1, e to the minus I Q4, x5 minus x2. I'm about to fall off the treadmill here. And then these are divided by Q1 squared minus m squared, Q2 squared minus m squared, and so on, Q3. Like this. And remember last time when we did the 1 case, there were only 2 propagators. There were only 2 of these denominators. But up here, we've got a factor of 4. We've got a product of 4. And that made the 0th order contribution 0 because we had 2 of these left. 2 of them canceled these poles exactly. But 2 of them were left over and give 0 for the ingoing or outgoing fields. Okay, so this is what we want to evaluate. I think I've correctly written the whole thing here. And now you just integrate like mad, right? Everything is going to either turn into Dirac delta functions, or you're integrating over a Dirac delta function. So all the integrals are easy. It's just a matter of keeping track of them. So keeping much better track than helps to do things twice. You know, the second time you get it right. So what are we going to get? I can pull out this minus I lambda over 2 pi to the 16th. Now, each time we get a Dirac delta function, that comes in with a factor of 2 pi to the 4th as well. So we're going to cancel most of those. So let's just do dx1. So we look, where do we have an x1? Okay, we're going to get a 2 pi to the 4th, del 4. It's always that. Then x1, we've got a minus k1. And these are symmetric, so I'm not worried about the overall sign, but I just read the sign from here, and I put that sign in the Dirac delta. It's just an easy way, mnemonic, to keep track. Then we have another x1 here, that's a plus q3. Okay, so far so good. Let's go on to x2. Now, all right, so x2, we've got a minus k2, and x2, where to go? Way down there, plus q4. And just keep going here. Okay, x3 integral. We get a p1. I'm doing x3, and the x3 is here. We get a minus q1. And now x4. P2 and minus Q2. Okay, times 2 pi to the 4th. Let's do x5. And x5. Let's see. Now we've got a whole bunch of those. They all occur in the propagators. So we're going to have Q1, that becomes plus Q2, minus Q3 here, and minus Q4. There. And then we still have D4 Q1, D4 Q2, D4 Q3, D4 Q4. And what exponentials have we eliminated? Let's see, have we got them all? I think all of these exponentials depend on x's. So all that's left are these inverse factors. Yeah, 4 of them. So this is the product of the, well, Q1 squared minus, Q1 squared minus m squared, Q2 squared minus m squared, Q3 squared minus m squared, Q4 squared minus m squared. Like that. Okay. We've just done 20 integrals. Woo! All right, so now we do 16 more, right? And you have to be a little bit careful here because the arguments of some of the delta functions depend on the arguments of others. So when we integrate here, okay, we're going to set Q3 equal to K1. We have to remember to do it here as well as here. So let's see, we also have 1, 2, 3, 4 factors of 2 pi, 5 factors of 2 pi. So I can cancel 4 of those and leave 1. So minus I lambda 2 pi to the 4th. Then what do we get? So we're gonna have this delta function left. Let's see. You think
integrals should drop out, right?
Yeah, that's what I was thinking. Yeah, I think we're going to be able to do all of them. So let's drop the integral and write del 4 here. So, all right. Yeah, then we have these denominators. So Q3 is going to become K1. So we have K1 squared minus m squared. And this delta Q3 is going to be K1, so we have a minus K1 somewhere in here. Let's just leave ourselves some space there. This is all just going to sort, right? So now integrating Q4, we're going to have a K2. Q4 comes in with a minus, so we have a minus K2. And down here, we're going to have K2 squared minus n squared. And I think you can see this is just gonna give conservation momentum and 4 terms that cancel those zeros. But let me take it a step at a time here. Q1 is going to be P1, so we have a P1 here, and down here we have a P1 squared minus m squared, and finally Q1 becomes P1, Q2 becomes P2, so we have a P2 squared minus m squared, and we get a plus P2 here. Okay, so this does everything you could hope, and it's nice and simple. It won't always be, but this one's nice and simple. Those products exactly cancel these 4 down here, and the thing we're left with, right, there's this normalization, which for this case is actually going to be 1, because this doesn't contribute until order lambda squared. We have a minus I lambda. We have 2 pi to the 4th times conservation of energy. The energy out minus the energy in has to be 0. So we get overall conservation of energy. We have no other factors, and We're done. That's it. We got it all on one board. Not so bad. So keeping track of things now we're going to do next order. And next order is going to introduce some new features. So yeah, are there any questions on this? I think, wow, you said it last time. That's pretty simple. There's, that's true of a lot of, it's true in quantum mechanics, it's true in quantum field theory, maybe even truer in quantum field theory. Each step is simple, but there are gazillions of steps, right? And so you've got to do your bookkeeping, because it's really easy to go wrong here. So yeah, I think this one is clear. Let me go to the next example, because and yeah, this is exactly what I got in my notes. Minus I lambda over z squared, 2 pi to the 4th times a Dirac delta giving conservation of momentum. And we're always going to write it that way, because we are always going to get it 2 pi to the 4th. We can always put in a 2 pi to the 4th if we want one, times Dirac delta and conservation of momentum. So one of our Dirac rules, Feynman rules is, says, okay, we always get that. So we don't even write it. We're going to define a matrix element. We're going to define this thing to be, a matrix element that we're interested in, initial to final, times 2 pi to the 4th times the delta function in conservation of energy. Del 4, the sum over all the momentum. So we'll just put that in the definition, and then we only have to calculate this thing. I don't know where I actually started doing that in the notes. I think I carry it through, all of these initial examples here, but we'll make that definition and just calculate that matrix element. Okay, now second order. Any questions? Everybody's good here, right? Yes, no, everybody happy? Now what I want to do is keep the top line here. In fact, okay, I'm going to erase the bottom stuff. You good here, Kevin? Are you done with the bottom? Okay, so I'm going to erase down here. But a lot of what's up above is going to be the same, because we're always going to have propagators. What they connect can change. So we won't always have, these 4 Ds. And what I want to look at is probably a cubic interaction at second order. So rather than jumping to a quartic interaction at 4th order where we've got 12 fields, this will keep us to what we have. If we have a 3 factorial and phi cubed here for the interaction, let me change that here. But the principle is the same. This is going to add 6 fields, so we're dealing with a product of 10 fields. We're going to have 5 propagators. And now let's look at the Feynman diagrams for what that could be. So now we have two factors of this. So in the exponential expansion, there's 1 over 2 factorial. Well, the minus sign is going to cancel away anyway, but we're going to have 2 factors like this. So we'll have a y1 and a y2. 2 separate integrals of phi cubed. But we have 2 particles coming in, 2 going out. Okay, so P1 and P2 out, K1 and K2 in. And eventually, rather than labeling coordinates, we're going to label these lines by momentum. But now, what can happen? Well, one thing that can happen, we have a vertex and it produces another field. And since we have 2 vertices, I've drawn this badly. I'm going to do it again. Drawing 1 foot lines an inch at a time isn't very elegant. So K1, K2 in, P1, P2 out. And we have 2 vertices at positions I'll call Y1 and let's keep it all X's, X5 and X6. Okay, so this is one thing that could happen, right? That's legal. We've got 2 points of interaction somewhere in space-time. We integrate over all space-time for where that actually occurs. And bear in mind, it doesn't actually occur. No one diagram actually occurs. What happens is a superposition of all of them. But we could also have, we could interchange those 2 outgoing lines so that P1 comes from X6 and P2 comes from X5. So here we're going to describe this with a D15 and a D25. But so we'll have a D15, a D25. Here's a D5 K1 and a D5 or D6 K2. And then we also have a propagator here, a D5-6. So this notation, what did I do? Let's call this X3 and X4 like we did before. So this is going to be a 4-5. This is going to be a 3-5. And this is going to be a 5-6. So that's one possible Feynman diagram we could draw, but or we could interchange those so that we have a D. This diagram has a D4-6 and a D3-5. Then 5-1, 6-2, and then a 5-6. But we can interchange those outgoing lines so we could have a D3-6 and a D4-5 with the same input. It's not ambiguous which ones come in. Okay, anybody see another diagram?
You can switch the in fields as well, right?
Yeah, okay, so this is if we bring this out as X3 and bring that out as X4. So we've interchanged the final states. Try this. So K1, K2, this is X1, X2. Can you see? Then call this X5, X6, and take the final states off of that. So this corresponds to a D51, D52, these 2 lines. Then there's a D56, and then these guys give a D36, D46. So we have 3 possible diagrams here. Each of these contributes to the matrix element at this order. And I'm asking you to do the other 2. I'm going to do one of these now, and for a problem, you'll do the last 2. They're all very similar. If you spot what momenta have to be conserved, you can almost write the answer down. But don't work through it. You've got to do all this mess of integrals at least a few times before you just extract the rules. Okay.
I was going to ask, is that kind of, I had a question about, so is that kind of the physical difference between these 2 is like there's momentum being exchanged in this top diagram between the left and the right side, whereas the bottom side, there's momentum conserved at each of these vertices. So it's like one is.
We'll find, that's going to be one of our rules is that momentum is conserved at all vertices. And we'll see that in the integrals we do. Let's take a look at that when we start doing these integrals, in these products. Well, okay, so X1 through X4 always occur here. But then in these propagators, at any one vertex, when we integrate over X5, all right, so anything with an X5 is going to come in at, at a single vertex and get integrated and give a delta function. So we're always going to get conservation of momentum at every vertex and overall. And yeah, before I start writing in the propagators and doing this, there are actually some more diagrams we can draw. And these are a little weird.
And I just had a follow-up question just on that. So
yeah,
is like
right.
is one of these kind of like an elastic collision and the other is an inelastic collision then? In these two diagrams is like the one's exchanging momentum, so maybe it's elastic, and the top one would be elastic and the bottom would be inelastic. Like,
well,
maybe those are the wrong words to use.
Let's see, elastic and inelastic.
Inelastic, there would only be one particle.
All of these
from an
conserve energy overall. So in that sense, these are all elastic collisions.
Okay.
Right. So yeah, nothing's dissipating here. The only time you do something inelastic, sometimes you'd like to look at let's see, what is it? You'd like to see an electron radiate a photon. No, that doesn't consider. Let's see. No, that's not right. What is it? Let's see, a decay. Yeah, the problem, there are certain decays, and I can't think of what right off, that you can't conserve momentum.
Double beta, probably.
Okay, so an electron-positron annihilation can never produce a single photon. Has to produce two, because you can always go to the rest frame of the collision and there's zero momentum, and a single photon can't have zero momentum. I mean, 3 momentum, right? So that's impossible. So you always get 2 photons off that annihilation. But one thing you can do is imagine a sink over here that exchanges a photon. So in a sense, you can handle an inelastic thing by soaking up the extra momentum with some nebulous blob, basically. So that is one thing that's done to handle. So if if a photon passes an atom and scatters and produces a spontaneous emission, all right, like you do that with a laser, then okay, well, that electron is going to transfer some momentum somehow, and you really only want it to scatter off 1 photon, so that momentum's got to go somewhere. But for another day.
So loops kind of take that idea, but more you can convey it. This top diagram has momentum being transferred from the left vertices, or the left vertices to the right, or not vertices, edges, the left edges to the right. There's a momentum exchange happening whereas in the bottom,
these two could split the momentum, right? Whatever momentum these had is now in this, right? But that can get split anyway at all up here.
Of course.
So where the momentum ends up, all you really know is it's overall conserved. But let me draw. You mentioned loops. So okay, suppose our particles actually don't interact, but over here we have a spontaneous production of 3 from that vertex and spontaneous absorption of it. That could happen. What keeps that from happening? Or you could have 2 non-interacting particles, and these could exchange a particle this way. So you have 2 cubic vertices here. So you can draw this kind of weird diagram. And with each of these, well, you could, these could come out the other way. So, you could interchange those final particles and still have those diagrams. So there are 4 diagrams with these are called disconnected diagrams. These are connected diagrams. We're mostly interested in connected diagrams, but we have to worry about what these loop contributions are. At 4th order, we're going to see things. What are they called? We see loops. We also see tadpoles. So a single line can come along, and in a 4th order interaction, you can have this kind of thing, modifying the overall well, measurable properties of just that effective propagator, and stuff like that. You could have these at all order, right? You could just have a whole line of these so-called tadpole diagrams, and they contribute an infinite amount. And so you renormalize. You say, what you measure includes those already, and it's it's strange and uncomfortable, but it has also been developed with mathematical rigor subsequently. People just sort of made this happen initially, but you can use some renormalization group theory to show that, this is a consistent way to handle this kind of a mathematical divergence. It's like, what is that Riemann sum that comes up to -1/12th or something? I mean, there are rigorous mathematical things where you get rid of some infinities and get a consistent residual. It's not actually an uncommon practice. So that's going to happen here, but right now I want to look at the connected diagrams. And I think the one I worked out is case 1. Let's see, let me see what I labeled this. Yeah, okay, so this one, I'm going to work out this one for you. And I've left the other 2 as exercises, but with well, you've seen these can be fairly quick. Okay, so what we have to do is a whole bunch of integrals. Let's see, we want this one, which is this 3rd one. So these are the propagators I want to write. And let's see if we can conserve space. So let's see, we're going to need, we need a dx6, d4x6, because we now have 6 points of interest. And then for the Q's, how many Q's did we end up with here? It looks to me like we need 5, is that right? Oh yeah, five propagators, so we have 5 Q's. So there's a D4, Q1, and D4, Q4, D4, Q5. So there are integrals. We're doing a cubic interaction to 2nd order. So our coefficient out here, we're going to have minus, let me get all of these coefficients. So minus I lambda squared over 2 factorial. I'm going to drop the 3 factorial because each of these points occurs 3 times and cancels those. Then 2 pi's, we're going to have 1 over 2 pi to the 4th 5 times, because we have 5 propagators. That's 2 pi to the, what? I have to multiply here. Let's see, 4 times 5 is 20, right? There. So that's a 20. Okay, and then propagators. All right, so we need a 5, 1. We need a 5, 2. we need a 5, 6. We need a 3, 6. And we need one more. Too much space, minus IQ5, then 4, 6, X4 minus X6. Don't let me forget that one. And then we'll have we have a Q5 squared minus M squared, and we have a Q6 squared minus M squared. 1, 2, 3, 4, 5. Whoops, I have too many. I either have too few of something or too many of something else. Let me see.
You added one factor in the numerator, but you added 2 in the denominator.
Yeah. We have we only have a Q. I'm thinking of the next problem probably. Wait, there are 2 points here, but there are only 5 Qs. That's it. Okay, and so 4, 6, 3, 6. Okay, there we go. Yeah, thanks. Good. All right, and I'm going to get this out of our way so we can do all these integrals. So this integral goes here. Then we have these numerator factors and the 1 over z squared. So, all right, we have d. We're still going to have the dq's. Like that. And then we're going to have 2 pi. Now the x's, we're doing 6 x's. So that sounds like about 24 factors of pi. If we cancel with these 20, that leaves us with 4. So that may handle those. There's minus I lambda squared over 2. And now we have just a bunch of direct deltas and these denominator things. Q1 squared minus M squared up to Q5 squared minus M squared. Okay. Now, del 4 at, okay, let's just take them one at a time. X1, we have a minus K1 plus Q1. Del 4. Okay, X2, we have minus K2. Then X2 here is plus Q2. Del 4 at, all right, X3, we're going to get a P1. And X3 here minus Q4. And then what do you bet we get a P2 here, and X4 here gives us a minus Q5. So P2 minus Q5. Is that right? Yeah. Okay. Oh, and then the 5 minus 6. Okay. So that's the first floor. The X5, nothing here, but X5, we're going to have minus Q1, minus Q2, minus Q3. That's it. And then finally, X6. Here's a Q5. Then we're doing X6, right? So that's going to be plus Q3 plus Q4. Does everyone agree? Have I got it? I think we're okay. We've got these denominator guys. we got that amplitude. The only thing we're missing is those, which will cancel some of these. So let's press on to the next line. And start doing Q integrals. So
the one thing we're missing is each of the exponential factors has a I term in front before we canceled them out
we
because
got,
it was
we got
one.
an extra one, right?
Yeah, we have one more.
So we have 5 propagators. So there's one extra I. Good. That's right. Okay. So now, okay, Q1, K1, Q2, K2, Q4, P1, Q5, P2. Those are going to cancel these things. So why don't I just write the matrix element here? I can put in the Z squared. We'll cancel those because they're going to cancel these 4 Q factors, Q1, Q2, Q4, and Q5. We still have, right, 1, 2, and 4, 5. We still have the Q3 integral to do. And so let me write that, D4, Q3. We've canceled all but one of these. We still have Q3 squared minus M squared. There's a 2 pi to the 4th. And we've done these top 4, but we still have these 2, del 4 minus Q1, Q2 minus Q3. Those might as well be pluses. Del 4 at Q5 plus Q3 plus Q4. Okay, so now we do Q3. Can you see down this slope? So I minus I lambda squared over 2z squared. Then we do the integral. There's 2 pi to the 4th. Then these get replaced by P. So Q1 has become K1. Q2 has become K2. Q5 has become P2. Q4 has become P1. So now we do the integral over Q3. We replace Q3 is equal to minus K1 minus K2. So we have del 4 of P1 plus P2 minus K1 minus K2. Whew, good. And a factor. And that factor, Q3, is, we can write it as either P1 plus K1 or, we can write it as P1 plus P2 or write it as K1 plus K2 because those pairs are equal. I'll put it here as K1 plus K2. The minus sign squares away, minus M squared, like that. So we get a factor. And let's see, have I integrated everything I wanted to? I think I have. Oh, yeah, this actually agrees with what's in the notes, which is very encouraging. Whew. All right, so we got it, okay, on one board. So that's, I feel sort of triumphant. It feels good to get to work through one of these. These are easy ones, guys. You know, it gets more intricate than this. And yet you see a lot of regularity to all this. So yes, you can handle a lot of this by rules. You just write down answers more and more quickly as you get used to working these. So then I've given you these two as exercises. If you do this one, then getting that one is just interchanging P1 and P2 in the answer. So that interchange is immediate. You don't have to rework all those integrals every time. You can just interchange those outgoing momenta and you'll be right. And then I asked you to do something that, yeah, I hope will teach you an important lesson about just how you apply these things. Suppose, right, the scattering amplitude is a superposition of all three of these, so you add them. And now, what have you got? Well, look at our answer down here. All right. The interesting new bit is this factor here, K1 plus K2, quantity squared. What is that? All right, we're on shell here. So K1 plus K2 squared, that's K1 squared plus K2 squared plus twice K1 dot K2. This is all four-dimensional, you know, this is special relativity. You guys know this backwards and forwards, right? Except you haven't used it enough in this kind of situation for it to feel quite, oh, I know this backwards and forwards yet, right? So I set out some specifics in this exercise. Suppose, right, now two of these terms are immediate. What's K1 squared? It's a forward momentum for a scalar field of mass m. What's the forward momentum squared? With c equals 1. And this funny signature, it's just m squared. Right, m squared c to the fourth, you know, back in relativity, we have a minus sign, but here it's just m squared. Is it clear? Right, e squared minus p squared, you know, p squared c squared. It's the usual energy momentum formula, but we're just after the magnitude of the four vector. The magnitude of a momentum four vector is m squared. They're the squared magnitude. So we get that twice because this is also a scalar, a Klein-Gordon scalar field with an interaction. And now this, okay, well, 2, you know what 2 is. Now, suppose K2 is at rest. Suppose we have a target at rest and we smack into it with K1. What's K2 look like? Yeah, you didn't expect to have to do this, right? You were just thinking delta functions and integrals. Yeah, you know, you want to figure out the physics at the end, right? I mean, we're going to calculate differential cross sections ultimately here somewhere. And, you know, you're going to end up with some four-dimensional integral, and you're going to write it as, you know, time and radial and angular stuff. And you're not going to integrate the angles because you want to find the angular dependence of the differential cross section. You know, d sigma d capital omega, right? How does the scattering cross section depend on angle? You want to be able to make those predictions. So, you know, you're actually going to need to work with some special relativity. Well, K2, the forward momentum of a particle is gamma, is m gamma, you know, CV, right? You can write the forward momentum this way. So if K2 is at rest, then there's no velocity and gamma is 1. So K2 is just m 0. Not so bad, right? So you just get to put an m here, and then you get K2, just the 0 component. Well, what's the 0 component of K2? M gamma. So you get an m squared, and you get a gamma for particle 1 here, right? So you get an overall m squared, and you get twice 1 plus gamma 1. Okay, so your second exercise in this section is, you know, given a sufficiently simplified case. Okay, the other thing I want you to notice, you know, what is the energy of the LHC? Roughly. Order of magnitude.
TeV.
Yeah, it's TeV. Tevatron is, I think it's up to like 14 TeV, you know, maybe as much as 10, you know, tens of TeV. Okay, TeV. Now, suppose you're colliding protons. What's m squared? What's m?
2G. 2G.
G. It's 1 GeV.
1 GeV.
Right, 2 protons, 2 GeV. M squared is a GeV squared. Right, and how do you find gamma? All right, so the energy is m gamma. Right, the mass is m, so if you take the energy over m, that's an easy way to find gamma. And if your energy is 10 TeV and m is 1 GeV, then gamma is 10,000, right? 10 to the fourth. Okay, so if I have something like this, 2m squared plus 2m squared gamma, that's 10 to the fourth, and that's 1. This is about equal to 2m squared gamma. Okay, masses become negligible in high energy particle physics. So, you know, if you've got you have an electron mass in a problem, it's called 0, unless it's multiplying, right? So, you know, to actually compute the differential cross sections we're interested in, very often you're able to set the masses to 0. So this exercise, yeah, I've just done half of it for you, so it'll be really easy now. But think it through, and you know, practice your special relativity a little bit, just to, you know, be sure you know how to reduce these things in that sense. It's you know, it's like not a fascinating undergraduate topic anymore. Now it's just a tool. You know, you got to be able to do special relativity. So, you know, little practice, you will.
And I'm sorry, I just forgot that in our notation, K1 and K2 were just the momentum of the incoming waves, right?
That's right. Yeah. Yeah.
Okay.
And okay, so in the exercise, I specify K2 at rest initially. All right, and that never happens anymore. People don't hit stationary targets; they do colliders. Right. So the lab frame is the center of mass frame, and you don't waste all your energy getting some stationary target moving. Right. I mean, the old cyclotrons and stuff used to impinge on a stationary target, and the amount of energy that actually goes into an interaction is greatly reduced because a lot of energy just goes to getting the target particle moving. And then there's some residual. So you do much better if you can get 2 protons to collide head on, or a proton, antiproton. At that energy, it doesn't make a whole lot of difference. So yeah, I think, let's see. Yeah, I think they set up Fermilab as a proton antiproton collider, and the LHC might just be proton on proton. I forget. I mean, you can build a storage ring and store a bunch of antiprotons. You do a bunch of collisions that produce antiprotons in abundance. You cycle them off, put them in a separate ring, and you can feed them into the ring in a counter-rotating way. I forget what the setup at CERN is, but then people bunch these things. It's not just a single proton. It's a batch of, I don't know how many, 1 million particles in a batch, or 1 billion. I'm not sure. But you want to make those groupings really tight, so you use up to, I think, typically up to octopole magnets to squeeze those protons together, even though that's not where they want to be, so that when the 2 beams pass, you actually have probability near 1 that you're going to get a collision. And, and then the data handling from a billion collisions per second gets to be a really interesting computer problem. The technology that goes into these detectors, these colliders, it's incredible stuff. And, you know, I wish I could tell you more about it. You know, I toured Fermilab and the linear accelerator at Stanford, but you know, they're just amazing devices and huge. You know, the detector, one of the detectors at CERN is the size of the physics building. It's the size of this here building. That's the detector. So anyway, I don't have time to do another example, but the next example I've written up in the notes. I should work through this because once again, some new features come in and some really interesting 4-dimensional geometry. So I'll work through that. Yeah, we have time
on
for
that last bit. Is there a way to see that effect? Just you were talking about the interaction. I guess I mean, the reason they're doing it is that it interacts strongly when you have 2 protons that are moving. So the laboratory frame, you know, being, I guess it's on the center of mass, the laboratory frame being in the center of mass of the system versus.
Yeah, they're the same. They're the same system for a head-on collision. Yeah.
Can you see why that's a stronger interaction in this Klein-Gordon field that we've just drawn up here in the first order interaction? Like why having the 2 in moving frames would be a stronger interaction, or is that something that just happens with fermionic fields? Or
No, that's just kinematics. Okay.
Yeah.
Let's try and work it out. Anybody need anything on the board here? I'll have to erase it before next time anyway. So yeah, let's.
Does it just make K1 plus K2 maximal or something? K2 plus K1 squared maximal, or yeah. Let's work it out.
I might have to write it out and see. Let's see what happens. Yeah, so if you have a straight head-on thing, that's probably an easy collision to work out. So if I have a particle at rest, you know, K2 say, and you know, K1 is coming in this way, then the total momentum, K1 plus K2, is M gamma, let's see, 1 B plus M 0. So you've got M times 1 plus gamma and M gamma V as the total for momentum. And you know, that has to be equal to P1 plus P2. And let's see, so if we suppose these are, so suppose afterward, if these are equal mass, you know, think of a pool table. Anybody wasted their time in a pool hall? You know, if you hit all right, you hit the cue square on to another ball, the cue stops and the other ball gets all the momentum, right? So what happens here is, well, at least at low velocity, relativistically, I'm not positive, but you're going to have K2 going off like this. Now, what you really, oh boy, let's see, how do we do this? What we want is P1, P2. You know, here, like, no energy has changed places. Nothing interesting has happened. What you really want to do is, let's see, in colliding these things, you know, so suppose they fuse. So 2 identical particles, but they're going to fuse into a particle of mass m, right? And m is going to be moving with for momentum M gamma 1 V final. All right, so yeah, this is yeah. Let's just look non-relativistically, right? You did the relativistic case for homework, but let's see if this is let's see M gamma. No, no, I've got it here. Okay, so let's see. The thing is, okay, momentum has to be conserved. So this is gamma final. So little m gamma initial times v has to be equal to the final momentum m gamma final v final, and that puts a limit on what this m can be. Let's see, energy conservation tells us that little m1 plus gamma initial has to equal m gamma final. So let's see, if I put this in gamma final here, v final, let's do it all in one dimension. We're going to have m gamma v initial over this is m1 plus gamma initial. So that mass cancels out. If the speed is close to the speed of light, maybe we'll make it ultra relativistic. This gamma is really large, and so basically, this is, oh boy, this is, let's see, let's divide by this gamma. So we have VI over 1 plus 1 over gamma, where this gamma is big. So V final is V initial 1 minus 1 over gamma I. So they're almost equal, right? The initial and final velocities are almost equal. And then we have M. Oh, let's see, what's the easiest way to get it? At big M is going to be little m 1 plus gamma I over m gamma final. I keep writing 5, gamma final, there we go. Okay, so no, solving for that. So I'm solving this for capital M. So it's little m times this ratio, but we just said that these velocities are almost equal, so this is almost equal to m times 1 plus 1 over gamma, right? That's a very small number. So your new mass can't be much bigger than the old mass. That's strongly limited.
Okay.
All right. So now, if we do it in the center of mass, right? Any question on this? Well, we're good. You okay, Tyler? Yeah. All right. So
Yeah, I'm just kind of listening in.
okay. Yeah. No, that's fine. That's great. And we're still recording, so everybody else can catch this too if they want. But now let's suppose we do this all in the center of mass, and two equal masses colliding. So here we've got m gamma times 1v plus m gamma 1 minus v. So the momentum is, the energy is 2m gamma and the momentum is 0. Right? Over here, same thing, the final velocity is 0. There's only one particle that's produced. So m is equal to 2m gamma, where gamma is big. So this gamma is as large as the energy you can produce, say tevatron 10 to the 4th times 2, and you can produce something much, much, much heavier than the particle you start with. So this is much, much greater than m. Whereas in this case, we could only get a little bit greater than M. So I think I maybe even did that correctly for the simple one-dimensional thing I wrote down.
Absolutely. Yeah, that seemed all right. So is there, I guess I was wondering if there's a way to, so I get that you would see more massive particles or more energy in this, but how does that directly translate into the interaction picture here then? Because I guess presumably they're looking for there to be like stronger interactions. They're looking for, yeah, that's I guess my question. What are they, why does that matter? I get why, but why?
Well, mostly, I think I know this one. It's mostly because the particles you're looking for, they're on the upper end of that weight scale, and so you need as much energy as possible in order to even see them.
But
Mostly because that's what they're looking for.
Does that mean in the interaction picture, like that there's higher order Feynman diagrams that are having vertices that have high enough probabilities that they're being measured, or yeah, how does it translate?
Okay, in QED, I think supercomputers are doing up to about 6th order, something like that. So when you predict the fine structure constant to 12 significant figures, you're probably doing 5th or 6th order Feynman diagrams. And that's consistent with what's measured. It's measured to 11 or 12 significant figures as well. But now, if you're trying to produce something like the Higgs with a mass of, what is that, 120 some GeV, you need, often these things are done by pair production. So let's suppose you want to produce, okay, let's go to the Stanford Linear Accelerator, and we're going to do a collision of electron-positron pairs to create a Z0 particle that's going to decay into a tau anti-tau. Right, so you want to produce a tau particle. Well, I forget what's the mass of a tau. It's like hundreds of GeV, isn't it? I forget. It's a really massive particle. So the energy of this thing has got to be at least twice the mass of the tau. Right, in order to produce 2 taus in the final state, you've got to have that much energy available. And even then, they're moving really slowly, apart. And to start seeing, dynamics or, these things are going to decay pretty quickly. Yeah, what are they going to do? This is going to emit I don't know, what will it emit? Let's see. Yeah, maybe it'll turn into like
Telepon,
and this will give you an electron, a positron antineutrino pair or something like that. You get some weak decay of this thing quite quickly. Well, it's easy to detect leptons in these detector magnets. That's always a really good signal that there's been a weak interaction, and they're easy to spot. But anyway, what was the question?
Yeah. So I guess
a lot of energy in this guy in order to use 2 taus.
And so is the problem maybe of thinking about it in terms of the Klein-Gordon field here, that it's got like no flavor, there's like no interesting subparticles in it. So this really the momentum is just the momentum, but maybe when you look at the fermionic or I guess I don't know what it would be, but in a more rich theory, then you could have the momentum is also an energy density that can then decay, like you've shown here, into other particles that you're measuring. So the linear accelerators are presumably trying to boost the frequency of these positron and anti-neutrino production, right? So that's why they're maximizing energy, is to get this tree to have a higher probability. Is that presumably it happens in nature all the time? It takes over the age of the universe to happen or something.
Yeah, or happens in stellar collapse or something, right? Or
something like that.
Something like that. But let's see. So, where do we see these kinds of energies? Early universe, certainly, or dynamic stellar events.
at Stanford, I think they've, you know, they're now, I think they've got parallel lines, one with E plus and one with E minus, so they can do head-on collisions there too now. But
Sounds like Stanford. They built it wrong the first time and then just spent money to build it twice. Sounds right.
well, no, a linear accelerator, you know, it's you need two of them to accelerate both electrons and positrons. Actually, it's, you know, it's actually more efficient to build two lines. That's what they did at CERN. At Fermilab, they actually accelerate the particles in. Let me think. How do they do it? Let's see. Do they have parallel beam lines? Yeah, I'm trying to think how it worked that they did it. Yeah, that, you know, you have nearby beam lines and you cross them where you want the collision.
Yeah. Is that a cyclotron?
No, let's see. The biggest cyclotron, I think, might be the second Triumph in Vancouver is the biggest, and the second largest is at Michigan State, and I think they get up to 250 or 300 some MeV.
Yeah. Okay.
Right. You don't use a cyclotron because you have to have a magnet, you know, as big as your outer ring. Right, you start in the center and the particles spiral out. Now, the advantage of a cyclotron is that it gives the same energy to each nucleon. So if you accelerate a heavy nucleon, you know, you strip all the electrons off of uranium or gold or something heavy, you know, so you've got, you know, 75 protons there. You're going to have a huge amount of energy. So if you accelerate some of those and smack them into each other, you get quark plasmas. You know, that's a way to put a whole lot of energy in one place. But the limitation is the size of the magnet. I think the Triumph magnet might be 30 meters across, something like that. I mean, it's big, right? You know, Google it, you'll see the pictures online. But no, what you need is a you know, a synchrotron where you increase the magnetic field. So you start off slow and you increase the strength of the magnets. Well, you know, that's totally passe. What's actually done is you never throw away an old synchrotron. So at CERN, you'll see they've got a small ring that, you know, feeds into a larger ring that then feeds into the big ring like that. So you accelerate it in stages. You get them up to a pretty high speed before you feed them into the big ring, so you don't ramp the magnetic field so far. And yeah, look at you know, an aerial diagram of CERN. You'll see a couple of smaller rings. Those sort of pre-accelerate. Yeah, I mean, pre-accelerate up to, you know, hundreds of GeV or something. Those are big accelerators in their own right. But by ramping the field, you just need the final ring diameter, which determines.
They use coils for confinement. Is that right? Inductors on the lines, as opposed to a central magnetic field.
They're long magnets. They're what are they? You know, like 10 meter long magnets like this. You know, that
Really? Okay.
yeah.
So they have
I'm not sure what the shape of these things is here, but your beam is running right through there, and you've got these long magnets like this, and I think these are like, I forget if they're 10 meters or 30 meters, but they're, you know, something on that kind of order. And so the actual curvature of the path happens in that, you know, 10 to 30 meter stretch, right? So it's a very small curvature because your circle is, you know, 27 kilometers around.
Okay.
And then between these guys, so you've got another pair of these guys over here, and between here you have a kick, a voltage kick that accelerate. That's where the particles accelerate between these, then they're curved here, then accelerated, then curved.
Oh, I see. Oh, I see.
Infinitely.
I see.
And yeah, and then the frequency. Okay, so these things are traveling at well, say TeV. So gamma is about 10 to the 4th. So let's see, what's the length of this ring? If it's 27 kilometers, is that a round or diameter? Kilometers. Yeah, suppose it's 30 kilometers around. So 30 kilometers is 3 times 10 to the 4th meters. But the length contraction goes like gamma, so that takes out the 10 to the 4th, and to one of these protons in that ring, it looks like it's 3 meters long. Right. So this thing's moving at the speed of light. So it does a full loop of the ring, and let's see. So 3 times 10 to the 8th meters per second into 3 meters is 10 to the minus 8th seconds to go around the ring once. These things are moving really fast. Yeah. It's this is the kind of playfulness with special relativity that you want to develop.
Okay.
You need to be comfortable enough throwing around gammas and V's that you never have to actually use a V very much. And it is a good approximation to say the velocity of these things is C, because it's within a part in 10 to the 5th of C or something like that. So.
Yeah, and then are we gonna? So is it in QED where you start talking about like particle decay and stuff? Then or
decay. Well, you'd like to see a proton decay. That'd be interesting.
Yeah.
But
that would be really great.
Well, mostly what people at the LHC are hoping to see now they're going to study properties of the Higgs. A rule of thumb in high energy physics is that today's discovery is tomorrow's background. So when they discovered like the Z naught, this is great news. Okay, we've seen the Z naught, and then the next iteration of energy, you're producing so many of them that they're really ugly, undesirable background to what you're really looking for next. Now the Higgs isn't quite background yet, but we're now at energies where we can produce the Higgs, and if you go up by a factor of 10, we're going to produce a lot of Higgs particles, and they may or may not be what you're trying to study. The sort of new discovery that people would be very excited by is some direct evidence for supersymmetry, to see a particle with, say, all the properties of an electron, except it's a scalar particle. The selectron, a supersymmetric particle to something, or a photino. Nobody knows what the lightest superpartner is, if it exists, but some particle should be the lightest, and if they really are there, they should show up in these accelerator experiments pretty soon. So you're trying to get enough center of mass energy that you could produce something very massive. Much like they did for the Higgs, but for some as yet unseen particle.
And I guess it's that production process, but I'm still a little interested. That's I guess what I'm confused and interested in.
Let's try some diagrams and see what kind of thing can happen. It depends on the specific interaction, and the interactions.
That's I guess
are predicted by gauge theory. Right. So far, that works beautifully. So you sort of think of colliding protons. So you've got a proton, and you might as well have another proton here, because that's not what collides. You've got two ups and a down here, and you've got two ups and a down here. So odds are you're looking at an up-up collision. You know, most of the time it's something like this. So the two particles coming into your Feynman diagram are a couple of up quarks.
Yeah.
Now, what do they do? Okay, depends on the time scale, but at a time scale of something like 10 to the minus 20 seconds, you're looking at strong interactions. And the simplest interaction is these guys exchange a gluon. All right, so that's your so-called tree level diagram. You've now, you know, there are lots of corrections. They could exchange two gluons, but gluons come from a gauge theory, an SU3 gauge theory, where the I equals 1, 2, 3, the field strength corresponding to the three colors of quark is okay. You've got potentials for each of these, and then you have probably a half and a structure constant for SU3, A, J, U, A, K, nu. So this is what the field strength looks like in a non-abelian gauge theory, where these are the structure constants of the Lie algebra of the relevant gauge group. So what this means is, right, in your action and in your Hamiltonian, you have F squared. So you're summing on I here, and you contract those guys. And so the kinetic term, you know, looks like, you know, A dot squared, right? That's the momentum squared stuff. But you're also going to have dA with a A and a C. And you're going to have 2 C's and 4 A's. Right? These are interaction terms. And they say that another thing that can happen in a strong interaction is that in this case, a gluon can turn into 2 gluons, or in this case, a gluon can turn into 3 gluons. So you get your up quark here, and you know, and that pair produces and sends gluon off there maybe, and you know, this gets absorbed, or you know, whatever. But this is the reason you can't separate quarks. If you try to pull 2 quarks apart inside a proton, say, or a meson, you know, you're putting energy into that system by stretching the spring. Basically, you're supplying energy to the system. That energy produces new gluons and makes the bonding tighter.
Yeah.
So anytime you try to separate a pair of quarks, you're actually just producing a whole lot more gluons that are making it harder to separate the quarks. So eventually what happens is, you know, one of those really energetic gluons just pair produces, you know, say a DD bar, and now you've got a DD bar meson that comes flying off. So you just produce this flood of mesons and baryons if you try to pull a couple quarks apart. So let's see. I went off talking. I forget what the question was.
Oh, this is good. How particle production just happens in an interaction scheme.
Yeah. Okay. So
really good.
Yeah. So what do you want to do here? Let's see. So yeah, it really depends what you want to produce, but you know, if you know, one really fruitful kind of interaction is if you can collide a particle with its antiparticle, because you know that produces a very energetic, almost anything neutral can come off. So you know, I suppose you could get, you know, like a glue ball off of this, or you could get a very energetic. Let's see, is that a possible interaction? Yeah, you'd have to look. You can, you know, this could certainly produce like a photon or a a Z0 like we had before. And that can produce any particle, antiparticle at all, right? So, you know, an energetic neutral particle can pair produce anything. And if it's got enough energy, that anything could be a very massive particle. Now, you know, there are other things that can happen. Your pair production, let's see, I don't know, what is it we want to produce? You know, you look at the available interactions. You ask, well, what kinds of things does that participate in? Well, okay, so the Higgs. Higgs is a scalar particle, but it's a doublet. So a complex doublet. So you have a gauge covariant derivative of acting on this doublet. So let's see, SU2, the interaction is going to have structure constant, and you know, you could have, say, a W plus and a W minus here. You know, that's a possible interaction term for the Higgs. So if you can produce W particles, well, you know, so maybe E plus E minus, or let's say, yeah, how about E minus, and you know, make that a pair of W minuses. So let's see, what is this going to do? Yeah, you like one of these to emit a W minus, and then it's going to send off like a neutrino. This W minus, via this interaction, can decay into a Higgs and another W minus. So you've got a vertex here with two W minuses and a Higgs, something like that. So something that causes whatever particle to emit a W. Now, any quark or lepton can emit a W. It's a weak interaction. Happens at a time scale 10 to the minus 11th, 10 to the minus 13 seconds, much slower than strong interactions. So I don't know how you would maximize the cross section, the probability for this particular interaction, but if you could get enough energy into this W, it could do that. It could do that decay. And then this is going to decay into probably an electron and a neutrino. You won't see the neutrino, but the electron is easy to detect and recognize as an electron.
So
yeah.
So the way they'd be doing these calculations is they'd be, you'd be doing the integrals, but you're doing Feynman diagram rules. So they'd be writing down these diagrams. They'd figure out what the propagators are in the Dirac fields at each of these vertices. They'd figure out a total measure for this picture at this order, and then they'd find the density of that picture in all of the possible schemes to whatever order.
Yeah,
is that right?
You've got to look at anything else that can happen, right? So you know, it may take, you know, many interactions, where by many we're talking on the order of billions or more, before you actually see the one you're interested in. So, you know, what happens, you know, realistically at CERN, what you see are jets, and you have various filters you put on the data that look for specific signals in those jets. So if you get you know, your quark collision, right? Well, you know, they don't collide. They start emitting gluons and things, and you know, what you would like is for something coming off of this to have enough energy to produce the particle you're interested in. You know, say a Higgs comes off of some kind of decay. But what you actually see, suppose you have a collision like that produces 3 energetic particles. You have your UN and your UN, and stuff happens here, but 3 particles come out. Right. So all of this happens in well, you know, the distance that particles travel in 10 to the minus 20 seconds when they're going the speed of light, which is not very far. But each of these things has roughly 1/3 of the 14 TeV. So it's, you know, these are still TeV particles. Those aren't stable, right? Those are going to decay. Those decay, and those decay particles decay, and those decay, and those decay. And so what you get are jets of particles. And now you're doing calorimetry. I mean, the big bulk at the outside of those detectors is basically a calorimeter that tries to stop everything and measure how much energy gets deposited after you've done a number of measurements on the way out to detect charge and momentum and whatever other properties you can detect. You then collect the total energy and the total angle. So the detectors come in layers. There's a vertex detector that's small. It tries to pinpoint where the interaction specifically happened. And you know, then you fairly far out, you can look for lepton products. Leptons are fairly easy to spot. And I don't know, I'm running out of what I know about particle detection at CERN, but I'm sure you could read lots about it online. There's so many issues that you run into detecting these things, but what they do, they put gates, right? You're getting probably on the order of a billion collisions per second. So in a billionth of a second, you right, that the products of that collision have traveled 10 to the 9th times, but it's 10 to the minus, wait, how much time before the next one? A billionth of a second. 10 to the minus 9th times 3 times 10 to the 8th is, you know, what, 3/10 of a second? In no, talking meters. What? Hang on. So you get a collision every 10 to the minus 9 seconds, and it travels at 3 times 10 to the 8th meters per second. So 0.3 meters is how far it goes. So okay, by the time these jets have traveled out, you know, 10 centimeters or so, a foot. All right, remember, this detector is the size of the SEER building, right? So by the time they've traveled out a foot, you have to decide whether you want to keep the data or not, because another collision has just happened. So that has to happen really fast. So you don't have all the data about a collision before you have to make a decision whether or not you've seen something interesting. So you have all these triggers set close in that look, okay, are there any leptons coming in? Are there any of this kind of thing, that kind of thing coming out? Is there an unusual number of particles coming out? To different interactions, you look for different signals, right? And you can tune your selection process to look for those. Now, in addition to that, I think they keep, at the LHC, they keep every 10,000th interaction.
Yes.
So yeah, so, you know, they're 10 to the 9th per second. So you're keeping, you know, 10 to the what, 5th, 10 to the 5th, you're just dumping the computer in case something unexpected happened. You're sampling it. But then you keep the ones that look like they're interesting, and then you make further decisions as it travels out and you gain more information. But even after the particles have penetrated the entire detector, remember this detector is, I don't know, 80 meters across or something. And you have to definitively decide whether to keep the data, but detectors on this side, you know, specific information from this side of the detector can't get to that side fast enough, right? Light travel time, 80 meters, you know, that's a huge long time compared to the time you've got to make a decision. So these decisions have to be, you know, queued in really quickly. And so then you store the data, it's dumped to this huge computer bank. You know, the computational capacity of these things is just enormous. And, you know, sorted, analyzed. You can Google I don't know. Often I think what you see is actually a modeling of what the first Higgs detection might look like, or you know, maybe you can find what the first Higgs detection actually looked at like. But you know, it's all these bright lines coming off. Thousands of particles were produced in the collision that saw the Higgs,
Yep.
and you have to track them all, right? You have to figure out, okay, where they all come from. You know, what led to this particular shower of particles. There are particles going every direction in that, you know. Really, you should Google that picture. It's just like, whoa. But anyway.
And a lot of them are invisible too, because they're not.
Oh yeah, you're not even
can't see
seeing
them.
neutrinos and stuff, right? Or the Z-naughts. You just see a gap in the data. But yeah, eventually these things get sorted. It's amazing stuff. So another question, or shall we call it an afternoon?
So I mean, I guess we're just going to do the same thing with drag fields, and that's the standard.
Oh yeah,
model, basically.
I mean, this is a precursor to what we'll be doing. Now, we're going to look at another interaction or two with these scalar fields, and from that, we're going to infer Feynman rules for dealing with interacting cubically or quartically interacting scalar fields. And it's a list of a half a dozen rules. Just write down this, write down this, write down this, write down this, and now you've got the matrix element, right? So it saves us writing out all these integrals all the time, because so much of the time they just lead to the same predictable stuff. Then we're going to formulate QED. So, writing the Dirac propagator, I think it's already in the notes. The Dirac propagator is easy to write. What's actually tricky is we need to do E&M in a covariant way. We wrote down the quantization of E&M, but we chose the Lorentz and Coulomb gauge to do that. And since the coupling between a Dirac particle and a photon is a gamma mu, a mu, we'd really like a mu to be covariant. And so I'm going to introduce one or two more alternative ways to covariantly quantize the electromagnetic field. I'm leaning now towards simple rather than ultimate. The best way to quantize gauge theories is using Brst symmetry, which is a lot like a supersymmetry. You extend the number of fields in your system so that you have a symmetry that is actually conserved throughout the whole interaction, and it's called Brst symmetry. And then there are certain natural constraints that occur in the field equations that actually impose the constraints that you're after. So it's a really cute trick, and it's really important to understand that for non-abelian gauge theories like the electroweak or the strong interactions. To do calculations there, you really need to do BRST quantization, but it involves bringing in anti-commuting numbers and fields and some things that just are a whole bunch more new stuff, when what we're really trying to do is get the rules for QED. And so there's an intermediate step closely related to the BRST, but not quite. What you do is you add a term, you know, 1 over something, d mu a mu. You add something like this to the electromagnetic interaction, and this is not gauge invariant, right? It breaks the gauge invariant, so you're carrying along non-physical modes of the vector potential, some things that are actually gauge, but you fix it in the end by, you know, taking an appropriate limit to impose the gauge condition at the end. And it gets rid of that term, and it makes it all gauge invariant, and it allows you to handle everything covariantly. So I'll probably do that sort of an intermediate treatment of E&M. Adding back to the E&M chapter, so we'll back up to, what was it, chapter 8 or something. I haven't written that yet, but we need that to then write the rules for QED. But then we're going to do some real scattering calculations. There aren't many scalar fields around, you know, just the Higgs really, or mesons, you know, those pions you can treat as scalars for some purposes. But you know, the corrections to Coulomb's law, right? You know, we'll be able to compute that and, you know, come up with an amazing amount of angular dependence of electron scattering. You know, comes out of just going to the next order in Feynman diagrams. So, you know, that's where we're headed. And so once we get rules for scalars, then we're going to do QED.
Awesome.
That's good.
I'm actually presenting at the research thing in just like
okay,
5 minutes.
Good. Well, yeah, break a leg. Yeah.
I'll try.
Talk to you later,
Thanks
Dr.
again.
Wheeler. See ya.
I'll see y'all.
Have a nice day. See you, Tyler.
You too.
Bye, Dr.